Okay, so the idea for a hash table, as name states, is that your data structure looks like a table. Okay, so what you see on the right of the screen is a table with rows and columns. So what you see in front of you is a single columned table with multiple rows. Each row is indexed starting from 0 going up to probably the size of the table. Now, what's going to happen is we would like to store some information in this table. Again, it depends on how you want to implement it, but let's say for the sake of understanding, we're trying to store strings. So whenever I provide a string to be stored in the hash table, it has to go through something called a hash function. A hash function. The hash function will take the string, is going to convert the string or generate a hash code. The hash code typically will tell you where to put the value or the string in the table. So example, let's say my string is it. It goes through the hash function. The hash function is going to give me 3. 3 is my hash code, which is telling me go and store string it at position number 3 in the table. So that's the whole idea of a hash table. Okay, so quickly, there's a hash table. You have a hash function that generates a hash code. Hash code is the index position in the table where you would go and store the string or the value. Now, what's so special about this approach is that this is really fast. Okay, so the runtime for this one would be constant. How so? So we're going to have a memory location, which is going to be the table itself. Okay, we can implement this thing using an array, for example. Next, whenever a value or a string that needs to be inserted in this hash table, whenever that comes in, it needs to go through the hash function. Typically, the hash function is a mathematical function. If you execute it, okay, it does not require any recursion or loops, so the runtime would be straight away a constant value. This generates a hash code, and then that hash code would be a position in the array or the symbol table or the hash table. You simply go to that particular position and insert the value or search the value or remove the value. So for all 3 of these operations, insertion, removal, and search, the runtime is going to be constant. Does that sound interesting so far?
Yes, it's very interesting.
Yeah, so for all the data structures that we have studied so far, this one appears to be the fastest, okay? At least from the first slide, there's some kind of promise, some kind of interesting attribute that the runtime would be constant, and we're excited about it.
So
Let's see how, yes.
Like, is it an array or is it like, what is it basically? Like,
Yeah,
how?
okay. The simplest way of looking at it is an array. Okay, a simple array. The background, there will be an array. But we're going to look at it. Okay.
Doctor, is hashing the same thing websites use for passwords?
Very good and interesting. Yes, hashing has a lots of application. One of the applications is storing passwords.
Okay.
It's also very commonly used in encryption, security, and so on. Right. Some issues with this data structure. Number one is the hash function itself. Like, it's going to be a simple mathematical formula, okay? But simple does not mean the best. You have to come up with a mathematical formula which is going to distribute your data evenly on the data. We're going to talk about this thing in a few minutes. Okay, we need to define some kind of an equality test. And how can we say that one value is comparable to another value? But we've studied this before. If I want to compare 2 things, there's only 3 options. Either the first thing is less than the second thing, or the first thing is larger than the second thing, or both of them are equal. Okay, so given this, we can easily write and define an equality method, which is going to take care of evaluating two expressions or two values. All right. Third issue that is going to happen is collision. Okay, so we're going to talk about this thing in detail. So let's say there's another string. Let's say the string is times. It goes through my hash table, my hash function. The hash function generates a code which is 3, identical to the code for the string int. Okay, so now this is a problem. We call this collision. Collision. Yani if two or more strings are generating, or the hash function is generating the same hash code for different strings, this means there's a problem. Now, this is very common in hash tables. So a solution is we have to look for either a different hash function, we have to improve the hash function, or we have to look at a different way of storing and indexing items in your hash table. Okay, so working with hash tables, we have to look at some trade-offs. This is really interesting and very important here. So if you want to reduce the number of collisions, a simple solution is to increase the size of your hash table. Make it very large, okay? If you have a very large space, this means there's almost no chance of collision, which means the runtime would be constant, which is desirable. But again, to get a constant runtime or a very fast runtime, we need to have lots of space available. But on the other hand, if there's not enough space available, it's going to create lots of collisions. Getting collisions is not bad in a sense, but it's going to negatively affect the performance. Yani your searching, insertion, and removal will become slower. Like how slow? Okay, how slow? It depends on experimental evaluation. But theoretically speaking, the worst case would be big O of n. Okay, so again, we'll talk about this thing. So don't worry if you're not following me. I've just described lots of interesting stuff, but we're going to cover this in detail a little bit later. Yes?
Like, how does it go from constant to big O of n? Like, it's two ends of the spectrum.
True. So again, it's all about managing your hash function and the space carefully. If you manage it properly, your runtime would be constant. If you do not manage it properly, okay, you can get something as worse as big O of n. So we'll see this thing in detail. Okay, so let's start with the first thing, which is hash function. What is a hash function, and how does that work? Okay, so a hash function is a simple mathematical function. You're going to provide it some kind of parameter or input. It's going to work with a data given to you, and it's going to come up with a value, usually an integer value, which would reflect into or as the index of the table, of the hash table. Okay, let's look at some examples. What's a good hash function and what's a bad hash function? So phone numbers. Okay, let me open my Jamboard. Phone numbers. So okay, so here in Saudi Arabia, mobile phone numbers usually start with 05. Okay, and then we have something 2, 3, 4, 5, and then you have some digits. Okay, something like this. So that's how your mobile phone number is constituted. The first 2 digits are almost constant. It's always 05. Okay, this one changes not very frequently. We have a few options. Okay, so we're talking about 053, 054, 055, 6, and so on. These change more frequently. Okay, so what I'm trying to say over here is if I pick 05, if I pick the first 3 digits, that's not a very good choice. If I pick the last 3 digits, that's going to be a better choice. Why? Because these are changing very frequently. So you can get anything from 000 to 999. So we have, theoretically speaking, 1,000 different possibilities. Here, if you pick the first 3 digits, you only have maybe 5, 6, 7 possibilities. So we like to go for something that is going to give us a more diverse, okay, more number of possibilities. So picking a hash function from the phone number, we can go with the last 3 digits. That would be better. Okay, another example.
Doctor, so we the bigger the size of the sample, the better the hash code or the hash function.
No, 2 things. First of all, your space needs to be large enough. Secondly, your hash function has to be good. If the hash function is diversifying your hash code, the frequency is higher, for example, 1,000 compared to 5 or 6. Okay, we like to go with this one. That's better. Second example, social security numbers. Okay, so your national ID number. So here in Saudi, it's 10 digits. Okay, so something like this: 109,826, 1234. Okay, so some of this is coding. Some of this is coding. So the first digit is telling you the nationality of the person. Okay, 1 means it's a Saudi, 2 means it's not a Saudi. And then we have the next 2 digits. Okay, so again, this is used for coding purposes, 0, 2. And this is a simple integer value. It goes with every new citizen, they get a unique number. Okay, so again, if you look at the first 3 digits, there's not a lots of possibilities here. If you look at the last 3 digits, that's giving you more possibilities. So I would pick this one for the hash code.
So, Doctor, what about the middle one? Like the 3 middle values?
3 middle ones? Okay. Think about this. Let's say I have these numbers, 1, 2, 3, 4. Okay. Look at the simpler example. So the next number will be 1, 2, 3, 5. 1, 2, 3, 6, 1, 2, 3, 7, 1, 2, 3, 8, and so on. You notice these are not changing very frequently. Only the last digit is changing more frequently. If you look at it at a bigger perspective, hundreds, okay, so you're going to get 4, 2, 4, 8, 5, 6, something like this. Okay, which is showing you that the second digit is also moving. But the one which is not changing very frequently is the first digit here, or the 1,000th integer. All right. So we'd like to go with something which is more diverse, okay, which allows your hash code to change very frequently.
So they're connected, and then like the last 3 digits are the main diverse sample.
Yeah, the values that change very often.
Okay.
Okay, now let me show you. In Java, if you have any object of any type, okay, if you do a dot hash code, okay, it's going to give you a 32-bit integer. You can try this in NetBeans if you like. Okay, create an object of any class. And whenever you say X, let's say your object is X dot, okay, the pull-down menu is going to show you the hash code, one of those options. So you can select the hash code and Java generates a hash code for you. So if it is a string, it's going to get a hash code. If it is a upper class integer or double or float, Okay, it's going to give you a hash code. So when we're comparing two hash codes, what happens is it simply compares the integer values of those objects. Okay, these, of course, these integer values are created by the hash codes. But how is this defined in Java? How does that work out? But by default, it gives you the memory location, okay, physical memory location of that object. So that's going to read something like 0x3258, something of this sort. Okay. Sometimes, okay, it depends from machine to machine. Sometimes it always gives you an integer value 17. Okay, 17. That's not a very good option. This means that you have to rewrite the hash code function. But for wrapper classes or for some of the classes, you're allowed to customize this. You can overload, you can define a method hash code, and you can overload the default method. Okay, if you're creating your own class, of course, you can write your own hash code method for this. So I'm going to give you some examples. This is how Java works. So this is the code for, well, pseudocode for the wrapper class integer. Okay, there's a hash code method that simply returns a value. So whatever is the address, okay, of this particular integer that's going to be returned. For Boolean, it always gives 1, 2, 3, 1 if it is true. If it is false, it always gives 1, 2, 3, 7. For double, okay, it uses a little bit of shifting, bit shifting. So we have a small formula over here. Okay, it does a 32-bit shift using XOR. I don't know if you're familiar with this statement. If you're not, that's okay. You can look it up on Google how this works. So we're doing shifting, bit shifting for the actual value of the double, and returns this, converts that to integer and returns it. Okay, this is string. How string works. So strings hash code is a bit complicated. What happens is if I pass it a string, let's say hello. Okay, or what you see on the screen is call, C-A-L-L. Okay, it will go and pick up the Unicode values for each of these characters, and then adds this thing to a formula. This is called Horner's method or Horner's formula. Okay, so a little computation, it gives you an integer value. So for example, call is going to give you the hash code 3045982. Okay, if you provided a different string, of course, the hash code would be different. Okay, so this is just the code for the same thing. Again, you don't have to really worry about this.
Doctor, these are like default codes, or like what is this?
Yeah, these are how they are implemented in Java.
Oh, okay.
Okay. So if you want to create your own hash code, let's say you have your own class called transaction, you want to create your own, so you can use something of this sort. Okay, it's just an example. Okay, so here are some guidelines. When you're writing your hash function, okay, consider these things so that you can have a good hash code generation. But combine each significant field using the 31x plus y rule. Okay, this is the formula that I showed you a few minutes ago. If the field is a primitive type, and which ones are primitives in Java? Integers, booleans, floats, doubles, characters. Okay, there's 8 of them. So use the wrapper type hash code. If the field is null, return 0. The field is a reference type, and it's an address, so you can use a hash code. Okay, can be applied recursively. If the field is an array, then you have to apply the hash code to each entry of the array. So we have the arrays.deep hash code method, default method built into Java. You can just simply call it. Okay, so in practice, this usually works well, but there's no guarantee. Okay, there's no guarantee. Um, okay, so what should be a good hash code? For the sake of simplicity in our class, okay, we're not going to go into too much detail. So rather what we'll do is we'll use very simplistic hash functions just to make sense. So I'm going to explain using my Jamboard here, okay, some examples and how this is going to work. So
Doctor,
yes,
there are different types of hash codes.
yeah, hash functions, different types of hash
No.
functions.
Are we
Okay.
going to talk about like the Java implementation of link hash or like linked hash?
No, no, no.
Oh, okay.
Okay, so what you see in front of you is just an array, some kind of an array which is going to store integer values. Right. So here's my data. Okay, I would like to store this data in my hash table. I have to go through a hash function. Okay, this is going to generate a hash code, which is going to determine where should I go and store this value. Right. Let's look at the hash function, a very simplistic hash function. Okay, let's say this is my hash function. Are you familiar with modulus?
Yes, yes.
Okay, so a very simplistic hash function. But let's say I would like to store these values in my hash table. I'd like to store 38, 19, 22, and 15. Okay, I would like to store these values in my hash table. So I will say something of this sort. I'll say hash table, okay, h equals new hash table. And then I'll simply say h dot insert 39 or 38. Okay, so what's going to happen now is 38 is my data. It will go to the hash function, which means that I have to apply this formula, 38 modulus 10. So 38 modulus 10 is going to give me 8.
Mm-hmm.
How? Remember this, 38 modulus 10?
Yeah, so 3.
Remainder is 8. Okay, so this is what we're looking for. So now my hash code is 8. Okay, the red one is hash code, which means I need to go to position 8 and simply go and insert this value over here, 38. If somebody says h dot search 38, okay, so in a linked list or a simple array, you would have to go and check every one of them.
Okay, so now it has
So that's going to give you a big O of n time. But here, what we're going to do is we're going to get the help of the hash function. So 38 modulus 10 is going to give me 8. I know for sure 38 is at position 8. I'll simply go and get it from there.
So, Doctor, if we insert another value in the position 8, it will replace it or will it shift it?
No, we're coming to it. We're coming to it. Let's just follow this now. Am I going too slow or?
Well, Doctor, no, it's like it's very simple, I think.
Okay, so for 19 mod 10 would be 9. Simply go and put 19 over here, 22 goes here, and 15 goes over here. Okay, so that's how things work. This is what gives it the runtime of big O of 1. Right, now obvious problems. What if your hash code is duplicated? For example, I give it 28. Okay, so 28 is going to give me a hash code of 8. I simply go to 8 and it's already taken. Something is there. So what should I do? I could overwrite it, which is not a good idea. Okay, so first of all, this is called collision. If there's a collision, we have to resolve it. We have to fix this issue. So we're going to study 2 different approaches on how to do this thing. let's get back to the slides. Okay. So the first approach for avoiding collision is separate chaining. Okay. So this is what we do. We're going to maintain a data structure that kind of looks like this. So we're going to have an array of linked lists. An array of linked lists. The array is going to be used for hashing purposes, and linked lists would be used for storing information. Okay, so idea is, for example, I would like to store x. X hashes to position 2. So instead of storing x on position 2, I would rather insert it in the linked list attached to position 2. Let's say next value I would like to insert is s. S also hashes to the same position, 2. Okay? Now, instead of overwriting anything, what we will do is we'll simply insert s in the beginning of the list. Okay? In the beginning of the list. This means that the runtime would still be constant. Does it make sense? Example. Okay, so we're going to have a hash table like this. Okay, again, we have a hash code that's going to tell us where to go. So let's say I would like to insert 38. Let's say my hash code is x modulus 10. Okay, it hashes to position 8, let's say. So we'll simply go and insert a value over here. Next, we would like to insert 28. Let's see, 28 also hashes to the same position. So we'll simply go and insert in the beginning. Okay, so 38 goes here, and this becomes 28.
Also,
Wait,
in the
beginning?
same position of the
That's
array.
why beginning?
Yes.
Remember in a single linked list when we were trying to insert something in the list?
Yeah. It's,
Insert in the beginning, the runtime would be constant.
mhm.
Okay, so that's the logic here. If you insert at the beginning, this means the runtime would be constant. If it is not in the beginning, let's say I'm searching something. Let's say I'm searching 38.
Okay.
So this hatches to 8, and we go and start looking for it. Okay, so the first one got 38. Now you need to go and check the next one. So
This will
this
take
is
time.
not one search. Okay, first we had to compute the hash code. Then we go and jump on the first node. That's not this one. So we go check the next one, and then the next one, and so on.
So yeah, they go man.
So if this kind of looks like this, okay, that's not good.
Mm.
All right. So that's why having a good hash function is important. We don't want to see something like this. Rather, we will like to see something which is evenly distributed. One thing here, one thing here, one here, one here. You don't want to have long chains like this.
By good function, you mean like a really unique function for each, so that each like element has its own place?
So a rule of thumb is to use, instead of 10, we use prime numbers.
Okay.
So hash codes, I have a few slides, we'll talk about this thing.
Yeah, isn't this what they do in encryption?
Exactly.
Mm.
We use prime numbers. So we have prime numbers like 1, 2, 1 is not really considered, so 2, 3, okay, 5, 7, 11, 13. So I'd like to go for something which is longer, more complicated. For example, 47, okay, 43, 37. So these numbers are good prime numbers. But why should we pick something which is very large like this? And it has to be a prime number. Because prime numbers are divisible by only 1 or themselves. Okay, so that's kind of guaranteeing a uniform distribution. Let's have a look at the slide. I think I've deleted that slide. Okay. Anyways, the idea is that we have to have a uniform distribution. Yeah, that's the one. So when we say uniformity, this is what it means. Imagine this is my space, and I have a ball and would like to toss it in one of these bins. Okay, each one of them is a bin. So we'd like to toss it. What's the probability that the ball will go in the same bin? So it depends on a few things. Number one is how many times you're going to throw the ball. Number two is how many bins are available. If you have lots of bins and few number of balls, okay, there's a very less chance that multiple balls will appear in the same bin. But if you look at the opposite case, if the space is small, I have only 3 or 4 bins, okay, and I have lots of data, lots of balls to throw. So most likely, each bin is going to count many balls.
Yes.
So with the hash function, what we're trying to do is we want to achieve uniformity. So look at this particular thing. These are hash value frequencies for whole worlds in this book. Okay, so these are all the different kinds of words and how many times do they appear. If something like this is not good, we don't want something like this. This is crazy. That's going to increase over runtime. We would rather have something like this, where you have lots of empty places, okay, and the balls or the values, the data is evenly distributed. But if you get something like this, that's also bad. Okay, all the data is in one place. Okay, so this is not uniformly distributed. This is all empty and all the data is in one side of. So this means there's something wrong with your hash code or hash function. You have to design it properly. Okay? Right. So let's get back to we're talking about separate chaining. Okay, so in separate chaining, this is how we resolve the collision. Whenever you have a colliding value, we'll simply go and insert it in a single linked list, which is attached to each of those positions in the array. Okay, so here's a little bit of implementation, how to do this. And again, you really don't have to worry about the code because it's predefined. Simply go and use that.
Doctor, you said we're going to do 2 solutions. We did collision with the linked list. Is there's another solution?
Yeah. So let's look at an example for separate chaining. Okay, so here's my hash function is equal to x modulus 10. Okay, I'd like to insert these values. Okay, here's your table. Sorry, the drawing is not very good today. Okay, now, so when we want to insert 38, it's going to hash to position 8. Go to position 8 and we go and insert 38 over here. Next is 19. So 19 modulus 10 hashes to position 9. So we go and put 19 over here. 12 goes here. Okay, 28 goes here. So we insert this thing in the beginning, which means the runtime would be a bit faster for insertion. Okay. And then 26 goes here. 72, again, this one we can 72 and 39. All right. So now if somebody wants to search for some value, let's say I'm searching for 19, simply use the hash code. It's going to generate, that's going to be generated from the hash function. So now we go here, check this one, it's available. Okay, that's not what we're looking for. Go to the next one. So within just 2 searches, we got something like this. Like, would it have an effect if your hash table was like this? Yeah, if your hash table, if hashing space is small, there's only 2 values. So most likely you're going to get longer chains.
Yes.
Okay, and that's not good because now the runtime is big O of n over 2.
Okay.
Imagining that, yeah, luckily not everything goes in the same bucket or same space. Like, does that mean that if I increase the space like this, should I have a bigger space? Let's say start from 0 to 100. Would that be better? Yeah. Most likely now your hash table is gonna look something like this. Most likely. Many places are empty, okay, but only some of them are taken. So searching for something or inserting or deleting would be really fast. So at most 1 or 2 comparisons and we're done over here. Compared to this one, which could be slower with the O of n over 2. Okay. So this is one way of resolving the collision called separate chaining. Let's look at the other approach, which is called linear probing. Oops, probing. Okay. Another name for linear probing is open addressing. So it's used also most of the time as linear probing or open addressing. All right. This was invented in 1953. Okay, the idea is if a slot is taken, you simply move to the next one. Okay, take its neighbor. Now this works with arrays. Okay, remember here, in this particular approach, we're not using linked lists. This is just an array, a very large array. Whenever we hash to some place, if it is empty, we take it. If it is not empty, we go and look for the next one. Okay, I'm going to show you a little bit of a simulation on how this works. Okay, we'll use the same data that we have over here. So imagine this is my array. Okay, so again, using the hash function, same hash function, x modulus 10. Okay, so 38 is going to hash to 8. So we go to position 8, and we're going to put 38 over here. Next is 19. So 19 hashes to 9. So we go and put 19 over here. 12 hashes to 2. 28 hashes to 8. Okay, this is taken. Okay, this is taken. So we're going to go and check the next one. 19 is also taken. Check the next one. So we rotate, go back to the top. 0 is empty. So we'll go and insert 28 over here. But remember, to get here, we had to do 2 extra probes. Okay, so we checked the next one, which was position 0, and then we went and inserted this over here. Okay, so this is the cost. Yani to insert 28, we had to do 2 extra probes. Okay, let's try 26 now. 26 hashes to position 6. So we'll go put 26 over here because it's empty. 72, but 2 is taken. So we go and check the next one, which is empty. So we'll go insert 72. Okay, this one had 1 extra probe. Next is 39. Okay, 39 is again taken. Go check the next one. That's also taken. Check the next one, which is empty. So we'll go and insert 39. And now again, this was 2 extra probes. Right, this is good and bad because now inserting is really easy. Simply go check the next one and we go and insert there. But now what if somebody wants to search? Let's say I'm searching for 39. So it's going to hash to position 9. And now this is not 39. Simply we cannot return this value. Okay, so we have to go and check the next one. Probe the next one. That's not the one. The next one, that's, okay, we found it. So now we're going to return it. So this means, again, the same thing. Every time we're going to go and find a value, if it is not in its position, we have to probe, check the next, and then the next, and then the next, and then the next. So this approach, okay, is not very efficient. Notice one thing. Let's keep inserting values in there, and let's see what happens to your performance. Okay, I would like to insert 24. Where does it go?
In 4?
Yeah, position 4. So we go and insert 24 over here. Okay, so again, this was 0 probes. Next is, let's insert 74. Where does that go?
Again 4, but like 1 more probe, so it goes to 5.
Okay, so hashes to 4, it's taken. So we go check the next one. And this is 1 extra probe. Okay, let's say now I would like to insert 20. Where does that go? So this hash is
0.
It's taken. So 1 probe, 2, 3, 4, 5, 6, 7, and 8. You go insert 20 over here. So you'll notice as the space shrinks, available space shrinks, this hash table becomes slower and slower and slower. Okay?
Yeah.
So that's
So
a
it's
problem.
very space dependent. Yeah.
This depends. Okay, it's a direct correlation with the space. If there's lots of space available, okay, it works well. But as the space shrinks, so what happens is we're going to get more and more collisions, which means we have to do more probes, which means your overall performance of this data structure will become slower. So what's the solution? Do we have a solution? Anybody?
Larger space.
Good, that's the solution. Larger
Like a
space.
very large space.
Every time the available space shrinks by half, you should double the size of your array.
Yes.
Remember, we cannot simply go and double the size of your array. This requires creating a new array of double the size and then copying stuff in the new array. Then
We can use an array list.
Sorry?
We can use an array list. It's already like an implementation.
Come on, array list. We studied this in the first week of the course. That's meaning you always overframe time.
Oh, okay. Then.
So yeah, working with the arrays, okay, with linear probing works fine as long as there's enough space available. But as the space shrinks, we're going to have problems, more collisions, and more number of probes. Okay. So if I look at this is the code for the linear probing approach. All right. So in linear probing, this is what happens most of the time. Even if we have a very large array, we're going to have something called clustering. which means we have a contiguous blocks of items. Okay, they start cluttering in one place. That's called cluster. So this is a little bit of a problem. Look at this simulation. So these are the values which are being inserted. Okay, G hash to position B, and then we have the probe 4 times. Okay, so you notice this is the problem with this particular approach. Because we're always inserting in the next position, okay, most likely we're going to clutter. And that's going to aggravate your problem, which means the performance will become even slower and slower and slower. So one solution is, hey, why should we always look at the next position? Why not maybe position +4 or position +8 or something of this sort? But that's going to make your life complicated. Look at T. Try to insert T, looking for a position. We're always looking for the next one. And notice we had to go through the entire array to find the position for T. Okay. Knuth was a scientist in the 1950s and 60s. Okay, many people simply call him Baba Knuth because he's considered as a father of algorithms. So he addressed this problem, and it's very well known. It goes by the name Knuth's parking problem. So when you're in a street, I'm sure all of you are drivers. When you're in a street and you like to park your car, okay, what we do is we come and we look for an empty place. Whenever there's an empty place, we'll move and park your car in there. So if you look at the picture in front of you, okay, this is the car and we like to park it. We have to displace to 3 positions. Check the next one, and the one after, which is available. So we go and put the car over here. Okay, so what we do is we do mean displacement of the car, which means if the array or the street is half full, okay, which means that we're going to have n over 2 cars. So the mean displacement would be given by 3 over 2. If it is full, can be given by this formula. Okay, this math behind it, I'm not going into too much depth. Okay, if you're really into it, you can go ahead and Google this stuff. Okay, this is the analysis of linear probing. All right. So here's a summary now for the hash tables. But for an average case, if you like to insert, delete, or search something from a hash table, okay, you can see the saying under uniform hashing assumption. When you have a large enough space and your hash function is very well written, it's uniformly distributing the data in the array, okay, or the hash table. In that case, the runtime will be almost constant.
Constant, yes.
Okay, so 3 to 5 maximum searches or operations, and then you're there. If it is not, okay, if it is not uniformly hashed,
it could reach the big O.
It's not good enough, or your space is limited. In that case, the guarantee is big O of n. Okay, and that's the worst case scenario for the hash table. So bottom line is this particular data structure, okay, either you implement it with separate chaining or with linear probing. Both approaches, you have to be careful with 2 things. Number 1 is space utilization. Number 2 is having a good hash function. Okay. So if I'm comparing separate chaining with linear probing, okay, separate chaining performance degrades gracefully. Okay, there's less clustering, but it can be there if your if your hash function is poorly designed. Linear probing, okay, there's less wasted space. It's better for cache performance, but this is good as long as there's plenty of space available. Okay, we have some other variants for linear probing or hashing, there's something called two-probe hashing. So we use two hash functions. There's also double hashing. Okay, so there's a video that I would like you to watch. I'll point to you to it in a few minutes. Okay, there's something called cuckoo hashing. This is also interesting. If you go ahead and look at it.
What's the difference between a double and a two probe?
All right, I think you should. This is my last slide, so
Okay.
let's start here. So, okay, what's a two-probe or double hash function? Double hashing. So here is my function. Let's say x modulus 10. Okay. What I'll do is I'll define another hash function, which is f of x. Whatever is the result of this function, we're going to mod it with another function.
Oh, okay.
Okay, so this is double hashing. So first you go through this hash function. Whatever you get, you go and hash it with the other function. So usually you pick a larger value here. Okay, let's say 191. And the second hash function is going to be a modulo with 17. So first would be a bigger number, then a smaller number. So the idea is that we want to have more uniformity in the data. Two probe means that instead of probing plus 1, what we do is we do a probe 5. Okay, how many times should we do it? This also depends on the formula. So you're going to write a formula which is going to tell, okay, if this the value is from A to D. Okay, let's say this is my key. Okay, then probe plus 2. If it is ending in E to K, probe 5. If it is from O to Z, probe 9. Get the idea? So again, this is another approach for having a uniform distribution.
Okay.
So both of these approaches are there to have a uniform distribution. Remember, we said this thing that if your hash function is not good enough, or your space is not well utilized, okay, in either case, runtime would be go of n.
And
To avoid that, we need to have a good hash function, and we need to have a good
space.
Resolution strategy.
Okay.
So either use the linear probing or using the separate chain.
So Doctor, as a good hash function, could we say, for example, modulo for all the prime numbers that are before the number itself?
Here's an example. I mean, what I put over here. So we can use double hashing. The first hash is with a very large prime number, and then the second hash is I can do it like this. Here's another approach, which is dividing the large table into multiple portions. Okay, so here's my table. I'll divide it in 4 portions. And now I have 2 hashing. Okay, I have 2 functions, h of x and f of x. Let's say each one of them is size 10. Okay, so 0 to 9, and then 0 to 9, and 0 to 9, and 0 to 9. Okay, so this is my basically hash table 0, hash table 1, hash table 2, and hash table 3. So the first hash function is going to determine which hash function should I go with. And the second one will tell me which position should I go to. So for example, I would like to store 38. Okay, 38. So this is telling me position 8. Okay. And modulus 4, if you modulate by 4,
is
it
the
will be 2.
So it's the second part.
Go to hash table number 2, go to position 8. Okay, and here we go and insert 38.
This is a really good solution.
Yeah, so this is 2-step hashing.